Hello everyone. A very good evening. I hope I'm audible and visible. So let's wait for 5 to 10 minutes so that everyone can join this session. So, okay, let's start the session. A very good evening and warm welcome to all of you. My name is Pooja Verma and PMRF Research Scholar from IIT Kharagpur, and instructor for this course is Professor Shamal Das Mandal, Advanced Technology Development Center, IIT Kharagpur. This is a week 9 live interactive session of signal processing techniques and its applications, where we will go through some assignment questions, some questions which is very similar to your assignment problem. I hope I am audible and visible, and are you able to see my slides? Okay, I hope all of you have gone through the lecture videos. So for this week, this is the content is related to the infinite impulse response filters. Okay, so first we will go through some concepts and formulas which will be helpful to solve a problem assignment questions. Okay. So infinite impulse response IR filters are used when speed is paramount and phase non-linearity is acceptable. FIR filters we are using where speed is not that much and there is no phase linearity. Okay, we are not able to accept when phase linearity is there. So IR filters are computationally more efficient than FIR filters as they require fewer coefficients due to the fact that they use feedback or poles. Okay, so the IR filters are more computationally efficient. So the general equation for IR filters are H of that is represented by this equation, that is H of Z is equal to B0 B1 Z inverse. This is for dash 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 B1 B2 Z to the power minus 2 plus some to the n number of Bn Z to the power n, and divided by 1 plus a1 z inverse plus dash am z to the power minus m, where the upper part is called the zeros and the lower part is called poles. So the compact form IFL filter can be written as like this: summation of k is equal to 0 to n bk z to the power minus k divided by 1 plus summation of k is equal to 0 to m ak z to the power minus of k. Okay, next. And the other one is the analog to digital filter conversion. Then traditional, what are the different traditional analog filters which we can design a filter? So there are two principal methods for analog to digital conversion. The first one is a bilinear transformation and second one is the impulse invariant method. And the traditional analog method which available for filter design, that is Butterworth filter design, Chebyshev filter design, and elliptic filter design. Mostly we will use Butterworth and Chebyshev filter design. There are two types of Chebyshev filter, that is type 1 Chebyshev filter design and type 2 Chebyshev filter design. Okay. Next, the first one is a Butterworth filter design. So the Butterworth filter design, the low pass Butterworth filter design filter can be represented as by this equation: mod of h of omega square is equal to 1 upon 1 plus e square in brackets omega divided by omega p to the power 2 to the power n, where e epsilon belongs to a ripple factor and omega is a 3 dB cutoff frequency. Okay, and if we want to find out the order, and this is very important, and every question that will be asked to find out the order of the filter, that can be find out by this equation, that is n must be greater than or equal to log 1 by del s minus 1 2 log omega s divided by omega p, where omega p is a pass band frequency and omega s is a stop band frequency, and this is a attenuation in the stop band 1 upon del S. Del S is the only the attenuation in the stop band. Okay. Next in the Chebyshev filter design. So already told you Chebyshev filter design are two types. Type 1 Chebyshev filter and type 2 Chebyshev filter. And that both Chebyshev filter is based on polynomials. So what are the equations of type 1 Chebyshev filter and type 2 Chebyshev filter? That is the magnitude square of the frequency response characteristics of a type 1 Chebyshev filter is defined as h of j omega square is equal to 1 by root of 1 epsilon square Tn square omega divided by omega p. This is a representation of Chebyshev type 1 filter. Next one is a type 2 Chebyshev filter. And the type 2 Chebyshev filter magnitude square response can be defined by this equation. That is mod of h of j omega square is equal to 1 by root of 1 plus epsilon in brackets Tn square omega s divided by omega p divided by Tn square omega s divided by omega p. Omega only, where epsilon is the ripple in the pass band and Tn is nth order Chebyshev polynomial. And the order of the filter can be find out by this equation, that is a log of in bracket 1 root of 1 minus del 2 square plus root 1 minus del 2 square 1 plus epsilon square in bracket close divided by epsilon del 2 whole divided by epsilon del 2 and divided by log omega s in brackets omega s divided by omega p plus root of omega s divided by omega p square minus of 1. And it also can be represented as cos inverse hyperbolic inverse del of e divided by cos hyperbolic inverse omega s divided by omega p. Okay. Just a minute. It's not okay. The other one is IR filter design. So in the IR filter design by impulse invariance method. So to design a IR filter having unit sample response h of n, that is a sampled version of the impulse response of the analog h a of t. Here h of n can be represented as a n of t. You have gone to I think previous lecture. This is digital domain representation of any signal. T is equal to small t is equal to n t. Okay, and any transfer function given in this form, that is h a of s is equal to summation k is equal to 1 to n ck s minus pk, where pk is the poles of a transfer function. Okay, so in order to find out the ck, we have to that coefficient ck, we have to ha of s minus pk at s is equal to pk, and then convert into ha of t by taking inverse Laplace transform. Then from there we have to convert in the digital domain. Okay, that is represent h of z is equal to k is equal to 1 to n ck pk, where this is a ck is a coefficient, constant coefficient, 1 divided by 1 minus e to the power pk t z inverse. Okay, so IR filter in the basically in IR filter we have to convert analog to digital domain in order to process any signal. The another method to conversion of or mapping from S domain to Z domain is a bilinear transformation. So basic principle of bilinear transform based on the trapezoidal formula for numerical integration. So any transfer function is given in this form in the analog domain ha of s is equal to b divided by s plus a. So in order to change the digital filter, we have to convert S domain to Z domain. That can be represented as a b divided by 2 by t 1 minus z inverse divided by 1 plus z inverse plus a, where S is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. And in that equation, we can also find out the value of z. That can be represented as 2 by t plus s divided by t by 2 minus of s. And from here we can get the that frequency also, digital and analog frequency, that can be omega is equal to 2 tan omega t by 2, and from here we can get this omega also 2 by t tan omega by 2. Okay, I hope that is the next. We will move to the assignment questions or problems. Just a minute. Actually, currently I'm not able to write on the screen, so I'm just reading from here that the questions, then we will solve. Okay. Okay, so this is the assignment 9. The first question, the transformation technique in which there is a one-to-one mapping from S domain to Z domain is. Option A is approximation of derivatives. Option B is impulse invariance method. Option C is bilinear transformation method. Option D is backward difference for the derivatives. So which one is the correct option? That in which there is an is one-to-one mapping from S domain to Z domain is. So for one-to-one mapping from S domain to Z domain, which technique we will use? Bilinear transformation. That one is a bilinear transformation. Okay, approximation of derivative is one to many mapping, impulse invariance also, and backward difference is not used for that. So bilinear transform is the correct option. That is it. For one-to-one mapping from S domain to Z domain, we will use the bilinear transformation method. Okay. So next question is convert analog filter into a digital filter with system function. The digital filter of is to have resonant frequency omega r, that is equal to pi by 2, used by bilinear transformation, and the transfer function is given as h of s is equal to s plus 0.1 divided by s plus 0.1 square whole square plus 16. Okay, so let's solve this question. So for bilinear transformer analog to digital domain conversion, as we know that the formula is S is equal to 2 by T 1 minus Z inverse divided by 1 plus Z inverse. right? So we have to put in place of s to this equation in order to convert into z domain. Okay, so already first we need to find out here that omega r is given. So we need to first take the digital frequency. We need to that can be calculated by this equation. Omega is equal to 2 by t tan that omega by 2. Here omega is given as omega r, so omega r. Okay, so first we will calculate that digital frequency. Omega is equal to 2 by t. So also we need to calculate t also, or in order to find out omega. Okay, first we calculate tan. Omega r is given by pi by 2 divided by 2, 2 by 2 t tan pi by 4. So what is the value of pi by 4? The pi by 4 is equal to 1. So it will be with 2 by t. Okay. So this is the relation between, for this question, omega is equal to 2 by t. As we see that the t is also not available. So we need to find out from anywhere, somewhere else. So first we need to find out the poles. Then from there we can find the. So what are the poles of that transfer function? The poles is the denominator part by putting equal to 0 plus 16, right, is equal to 0. So what will that is s square plus, if we open that bracket, 0 0.01 plus 2s plus 0.2s, that is 16, is equal to 0, right? So s square plus 0.2s plus 16.01 is equal to 0. Now we need to find out the poles. So already you know that how to find out, that is equation minus p plus minus under root b square minus 4ac. From here you can find out divided by 2a. Find out the poles of the transfer function. Now I am taking the other slide because we are not able to solve it here. So after getting the poles are s is equal to minus b. What is the value of minus b? Minus b is 0.2 minus 0.2 plus minus b square, that is 0.2 square minus 4ac. 4, a is 1 and c is 16.01 divided by 2. 2a is 1. Okay, if you solve that, you will get s1 and s2. What you will get? After solving, you will get minus 0.1 plus minus j4. Okay, here we will get both the poles s1 and s2. S1 is minus 0.1 plus j4 and s2 is minus 0.1 minus j4. If we and we also know that h is equal to sigma plus j omega, right? So if we compare that, so we will get omega from here, that is 4, right? Now put that omega in that equation, in this one, which we can we have find the relation. Okay, in order to find out the value of t. Already you know that we have got the omega is equal to 4. So from here 2 by t. So t we will get 1 by 2 or 0.5. right? So already we have solved that omega is equal to 2 by t. So here omega is 4, got, so 2 by t, and t is equal to, we will get 1 by 2 or 0.5. Okay, now we have got the t also, so we can put the value of t in that equation, that is where it is s is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. Now what will be the value of s? 4 1 minus z inverse divided by 1 plus z inverse. Okay, now we need to put that s value in that transfer function equation. So I have to erase it from here, then again solve it. Okay, so I hope all of you have noted down. Someone is asking something? Okay, sure. Now what is the equation of that transfer function? That is h of s is equal to s plus 0.1, right, s plus 0.1 whole square plus 16. Okay, now open this uh, here also in order to put the value of z, sorry, s 0.1 divided by s square plus 2, not 2, 0.2 s, that is 0.2, 2ab, that is, then 0.01 plus 16. Okay, so s plus 0.1 divided by the whole transfer function will look like s square plus 0.2 s plus 16.01. Now put that s value into this equation in order to find out the z domain or in the digital domain. So 4 1 minus z inverse divided by 1 plus z inverse plus 0.1, here 4 4 the 16, I am directly, that is a square, so I am squaring it here, 1 minus z inverse divided by 1 plus z inverse whole square plus 0.2 into, in place of s we have to put that equation into 4, that is multiplied by 4, 1 minus z inverse plus 1 plus divided by 1 plus z inverse plus 16.01. Okay, so now I'm moving from here so that we can solve the whole question. Okay, so now solve this equation in order to find out the solution. So here it is 4 1 minus z inverse. Now we have to multiply this 1 plus z inverse to this in order to find out the solve the question. 1 plus z inverse and take common, then after, okay, 1 plus z inverse and divided by whole 16. Now we have to solve the lower part also. 1 minus z inverse square, and that is also square, and now multiplying this with this, that is 0.8. So it is a whole square, so 1 plus z inverse and 1 plus z inverse will be cancelled out. So what left here? 1 minus z inverse and 1 plus z inverse. Okay, plus 16.01, 1 plus z inverse square, that is divided by 1 plus z inverse square. You can take here also square. No, already we have divided and multiplied, so it will go up. This 1 plus z inverse, which is in a lower part, it will go up. That 1 plus 1 is cancelled and 1 multiplied with this. Okay, I hope all of you getting. So if we remove from here, so what left? Only in whole equation. Here 1 plus z inverse whole square, and here multiplied by 1 minus 1 plus z inverse only. Okay, now if you solve the whole equation, then it is 4 1 minus z inverse in brackets 1 plus z inverse in another bracket. Now we have to multiply, and what left? 1 minus z to the power minus of 2 only, because 1 multiplied by 1 plus z inverse and minus z inverse minus z to the power minus 2, that minus z inverse plus z inverse will be cancelled out. Only 1 minus z to the power minus 2 will left here. Okay, now we have to open this equation also. 0.1 1 plus z inverse whole square, so 1 plus z to the power minus 2 plus 2 z inverse. Similarly, we have to do in the lower part also. So there is space issue, so I am solving it, or you can also solve it. So if you open that 1 minus z inverse whole square, that will be 1 plus z to the power minus 2 minus 2 z inverse, and that is 0.8 in brackets for 1 minus z inverse and multiplied by 1 plus z inverse. What left? 1 minus z to the power minus of 2, and after that from here 16.01 1 plus z inverse whole square. If you open, that is 1 plus z to the power minus 2 minus, or sorry, plus to the power z inverse. Okay, so now again we need a space, so I am removing from here. You can solve this question parallelly also. That will be easier to understand. Okay, now we have to that multiply these numbers inside the bracket and then add. Okay, so after doing all those things, what we will get? I am writing here already. I have solved. You can now, this is general equation. You can also solve it. So what left? 3.1. Okay, so I'm calculating it. Okay, so it will be 4 minus, if we multiply 4 minus z to the power minus 2 plus 0.1 plus 0.1 z to the power minus 2 plus 0.2, 0.1 multiplied by 2, that is 2, z to power inverse. Okay, then in the denominator, what is it? Value 16 plus 16 z to the power minus 2 minus 32 z inverse plus 0.8 minus 0.8 z to the power minus 2, I think, yeah. This point 2. Oh, 4 is also there. Here is 4. 40 is there. 4. Yeah. Here we are. I forgot to add here. There must be a 4 also. So the value will be here. If you multiply it here 4 into 0.8. So it will get 3.2. Here 4 into 0.852. So 3.2. That one is plus minus 3.2 z to the power minus of 2. Now plus 16.01. After that I am writing here. I am just multiplying with these numbers. 16.01 z to the power minus 2 plus if you 16.01 multiplied by 2, that will be 32.02 z inverse. Okay, now if we solve that, we will get 4.1 here, 4 point plus 0.1, 4.1 plus 0.2 z inverse plus minus 4 point z to the 4 multiplied z to the power minus 2 plus 0.1 z to the power minus 2. What we will get? Minus, here we will get minus 3.9 z to the power minus of 2. Similarly, in the denominator, we will get 16 plus where 16.01. What we will get? 32.01 plus here 3.2 is also there. So total 35.21 we will get, plus by adding and the whole part we will get, that is 0.02 z inverse plus 28.81 z to the power minus 2. Okay, take all the terms. 32 minus z inverse here and 32.02 Z inverse. So if you use 0.02 Z inverse, and similarly for Z to the power minus 2 also. So from here we will get this equation. Now we have to normalize this equation. We have to take 1 here, so divided by, in denominator and numerator and denominator both, divide by 35.21, then we will get that approximate value 0.128 plus 0.006 Z inverse minus 0.112 Z to the power minus 2. We have to divide that 35.21 in whole, denominator and numerator. Then here we will get 1 plus, that is 0.0006 Z inverse plus 0.9 Z to the power minus of 2. Now it has been normalized, then we need to find which option will be matching. So for approximately it is matching to option A, right? 0.128 plus 0.006 Z inverse minus 0.122, where we are getting 0.112, but that is, there is some calculation or something. So correct option is option A. We need to solve this question like this. Okay, and please carry one calculator with you, so that calculation will be can be done easily. You can calculate it parallelly also. Okay, so I hope all of you got this. So we can move to the next question. Okay, yes, yes. So the next question is, which of the following is true about type 1 Chebyshev filter? So which option is correct for type 1 Chebyshev filter? First option is equiripple behavior in a pass band. Option B is monotonic characteristic in the stop band. Option C is equiripple behavior in the pass band and monotonic characteristics in stop band. And option D is none of the mentioned. So which option is true for type 1 Chebyshev filter? So for Chebyshev type 1 filter, the equiripple behavior we have find in the pass band and monotonic characteristic in the stop band. And you will go through the slides. So there is a describe. So correct option is option C. Okay. So for type 1 Chebyshev filter, equiripple behavior in the pass band and monotonic behavior in the stop band. Okay. Now the next question is, using the bilinear transformation, determine the order n and cutoff frequency omega c of the analog prototype filter for the following discrete time design. So for that the specification is given. Pass band is 8 kHz, stop band frequency is 9 kHz, pass band ripple 0.5 dB, and stop band attenuation is given 40 dB, and sampling frequency fs is given as 44 kHz. So okay, let's solve this question. First we need to find out, we have to design a discrete time design. So first we need to find out the analog, that omega, we need to find out the order and the cutoff frequency. In order to find out, first fp and fs is given, pass band frequency and stop band frequency. It is given in kilohertz. Now we need to change in the radian per second. So let's calculate the omega p and omega s first, then solve the problem. So to solve this question, we need to use the bilinear transformation. Okay. So how we will get, that is 2 pi fp divided by the sampling frequency. Already this is basic one. So already I hope all of you gone through that. So fp is given, that is 8 kilohertz. So 2 into pi into 8 kilohertz, 10 to the power 3. Fs is given 44 kilohertz. So if we solve that, so 2 multiplied by pi value here, we will take 3.14 standard, and 8 then divide by 44. Here 10 to the power 3, 10 to the power will be cancelled. So we will get 1.142 radian per second, right? Similarly, we have to calculate the omega s also. That will be get 2 pi fs, that is fs small s, stop band frequency, that is, and this f here capital S, that is a sampling frequency. Okay. So 2 multiplied by pi value is 3.14, and stop band frequency is given in 9 kilohertz. 9 into 10 to the power 3 divided by fs, that is 44 kilohertz. 10 to the power 3. So this will be cancelled. If you multiply and divide with, so we will get 1.285. Okay, after finding out that omega p and omega s, that is the analog frequency, now we have to find out this omega, also omega p and omega s, by using the bilinear transformation. So already we know that how we will get from the formula 2 by t, where t is 1 by fs. So if we'll take that 1 by fs, t is equal to 1 by fs, so 2 into fs. Okay, so I am writing here. Okay, we will tan omega p, that omega divided by 2. So we can write it all like this also, 2 into fs, that is sampling frequency, omega p divided by 2. Now putting all the values and multiplying and getting 2 into 44 kilohertz, 10 to the power 3, tan omega p, what we 1.142 divided by 2. If you solve this, you will get 56554.2 radian per second. Okay. Similarly, we have to find out the omega s also in the stop band. So already I hope all of you noted down. Can I remove this part? Okay, that omega s will be required. So from here we can also get 2 into fs, tan here omega s divided by 2, that omega s divided by 2. So 2 into that one 44 kilohertz, tan omega is 1.285 divided by 2. If you solve this, you will get, I'm removing from here this one, you will get 65,876 radian per second. Okay, and here also I hope all of you noted down. Can I remove this part now, or should I? No, I don't have another slide. So I'm removing from here. Okay, Now we have got that omega p and omega s. Now what other things are given? That is passband ripple and stopband attenuation is given. It is given in the dB. Now first we need to change it from dB. Then we will calculate. Passband ripple is given 0.5. So 0.5 is equal to 20 log, that is minus 20 log of passband ripple is there. So del of P. Okay. So del of P you will get 10 to the power, that is minus 0.5 divided by 20, right? And if you solve this you will get 0.944. You can solve it in your calculator. I am writing here, I already solved this. Okay, so that passband ripple you will get 0.944. And now what we need to find out, the passband ripple we have get. Similarly the stop band attenuation also we need to change it. So if you del s, we need to 20 log del s is equal to 40 dB. That is, you will get del s if you solve 0.01 if you change it from dB. Okay, so now we have got the omega p, omega s, that del p and del s, passband ripple and stop band attenuation. Now we have to calculate the order of the filter using the bilinear transformation. Okay, so I need a space, so I am removing from it from here. So you can keep that these values in order to solve the other equations. Okay, I am removing all the parts. I hope all of you noted down. Okay, now what is the formula for determining the value of order of the filter? That is, n must be greater than equal to log 1 minus del s square epsilon del s square divided by 2 log omega s divided by omega p, in order to find out the order of the bilinear transformation function. Now we need to calculate that epsilon also. So what is the formula to calculate epsilon? That is, E is equal to, if the passband ripple or stop band attenuation, it is directly given the 3 dB down passband ripple, then epsilon is automatically, if E is equal, we will take E is equal to 1. If it is not given 3 dB down, then we have to calculate that epsilon. Okay, so formula for calculating this is 1 upon del P whole square minus of 1. Okay, so already we have to we already we got the del P, that is 0.944 whole square minus 1 of root. If you solve this you will get 0.349 value of epsilon. Now put all these values in this equation. Then n is equal to log 1 minus del S is 0.01. We have got square. Epsilon is given as 0.349 whole square. Del S is given as how much we have calculated. That is 0.01. Yeah, 0.01 whole square. Okay, and that is divided by 2 log omega s divided by omega c. Omega s is we have calculated 65,876 and omega p is 56,554.2. Now we need to calculate these values. So from here you will get if you solve all these things, so you will get 4.914, and in the lower part you will get 0.132. You can solve it, and if you divide this you will get 37.22. That is, if order must be greater than this 37.22, so n will be 38. Okay, so order of the filter we will get 38. Now how we will get the cutoff frequency? We have got the order of the filter, right? Now we need to find out the cutoff frequency. So how we will find out? So can I remove this one? Have you noted down? I hope all of you have noted down. So I am removing this. Okay. So okay, how we can get the cutoff frequency? The equation for determining the cutoff frequency, that is cutoff frequency is represented by omega c. Here, so omega c is equal to omega p divided by epsilon 1 by n. So omega p already we know that 56,554 divided by 2. Epsilon also we have got 0.349, and order of the filter, that is 138. So 1 by n, so 1 by 38 here. So if you solve this equation, the lower part you will get 0.973. You can check it, or if you divide this you will get 58,123.5. Okay, this value, only this value you will get 0.973, and after dividing with this you will get 58,123. That is, cutoff frequency is 58,123.5 hertz. Okay, so I hope all of you understand this question. Can we move to the next question? There is a lot of calculation needed for these questions, so already you can take one calculator with you also. Okay, so moving to the next question. The next question: determine the order of type 1 low pass Chebyshev filter that has a 1 dB ripple in the pass band, and in the pass band frequency is omega p is equal to 1005, and a stop band frequency is given 2005, and an attenuation of in the stop band is 40 dB or more. So here also we need to find out the order of a filter, Chebyshev filter. So what the things is given, omega p is given and omega s is also given, and in the pass band attenuation is 1 dB and in the stop band that is 40 dB. First we need to change it from the dB. So how you will get? So in, what is the equation for Chebyshev order to find out the order of the Chebyshev filter? That is n is must be greater than equal to log in brackets root 1 minus del 2 square, right, plus 1 plus del 2 whole square plus 1 plus e epsilon square this till this it is in root, then close the bracket plus e del 2. No, it is not plus, it is divided by epsilon del of 2. Okay, then divided by log in bracket omega s divided by omega p plus root omega s divided by omega p whole square minus of 1 in that root, bracket closed. Okay, now what we need, omega s and omega p is already given. We need to find out the stop band attenuation in order to solve this question, because here only del 2 is required, that is del 2. So it is given 40 dB. So already we have solved it. If you solve this 20 log del 2, that is minus 20 log del 2 is equal to 40 dB. So if you solve this, you will get 0.01. Okay. Now what we need to find out are the epsilon. So epsilon is the equation for epsilon is, you can find out by this equation. Just that is, it is also given in dB. So 10 log 1 plus e square, it is a pass, it is in the pass band attenuation is given 1 dB. So from here if you solve this, 1 plus e square 1 by 10, that is 0.1. So if you solve this equation, you will get e is equal to 0.5088. Okay, now we need to put all these values in this equation in order to find out the order of the filter. So I am removing it from here so that we can solve this question. Okay, so log bracket root 1 minus del 2. Del 2 is given 0.01 square plus 1 plus del 2 square, that is again 0.01 square in multiplication with 1 plus e epsilon square, epsilon we will get 0.5088 square, bracket closed, divided by epsilon del 2. So epsilon 0.5088 and del 2 multiplied 0.01. I am writing here. Are you able to see that? Or I can write here. Now divided by, that is log omega s is given, stop band frequency is given 2000 pi and pass band frequency is given 1000 pi plus root 2000 pi divided by 1000 pi whole square minus of 1. Now, if you solve the numerator part, you will get log 1 minus. Now we need to solve this. So if you solve this, you will get approximately order of the filter 5. Okay, 4 point, that is 0.7. So it is n must be greater than equal to, so it is 5. So correct option is V. Okay, if you solve this equation, that is 2 here, root 2 here, log 3 value if you find out, that is, I need to solve it also. I directly calculated in the calculator. So if you solve it, you will get 5. Okay, are you solving this? Should I hope all of you got that value. If you put all these values in this equation and solve in the question, all this, so you will get 4 point something values, that is equal to 5. So correct answer is option B. Okay. Okay. So moving to the next question. So which of the following methods are used to convert analog filter into a digital filter? What are the methods that is used to convert the analog filter into a digital filter? Option A is approximation of derivatives. Option B is bilinear transformation. Option C is impulse invariance method. Option D is all of the mentioned. So all these methods are used to convert analog filter into a digital domain. So the correct option is option D. All the options are used for converting analog to digital filter. Okay. The next question is, what is the duration of unit sample response of a digital filter? Option A is finite, option B is infinite, option C is impulsive. Impulsive means very small value, and option D is 0. So what is the duration of unit sample response of a digital filter? The unit sample response of any filter is infinite only. Okay. So the correct option is infinite duration. Okay. Can we move to the next question? Are you getting? Okay. So next question is, the Chebyshev filters have flat band, flat pass band. Option second is flat stop band. Op 3 is equiripple pass band, and 4 is tapering stop band. So in the Chebyshev filter, what are the it is either flat pass band or equiripple pass band or flat stop band and tapering stop band. So in the Chebyshev filter, we have flat stop band and equiripple in the pass band. There is two types of Chebyshev filter. So now, based on the options, we have to choose. Okay. So option A is 1 or 2 are correct. Option B is 2 and 4 are correct. Option C is 2 and 3 are correct. And option D is all the 4 are correct. So in the Chebyshev filter, here flat stop band and equiripple in the pass band. The correct option is C. Okay. If you see the frequency response of the Chebyshev filter. Next question is, the antisymmetric condition with M even is not used in the design of which of the following linear phase FIR filter? Low pass, high pass, option C is band pass, or in the option D is band pass. So in the low pass, the antisymmetric condition with M even is not used to design any linear phase FIR filter. The correct option is option A. Okay. So moving to the next question, the antisymmetric condition is not used in the design of a low pass linear phase FIR filter. Is true or false? The antisymmetric condition is not used in the design of a low-pass linear phase FIR filter. It is true. Antisymmetric condition is not used for designing a low-pass FIR linear phase FIR filter. Okay, the correct option is A. These are the theoretical questions which I hope all of you gone through the video lectures. So I'm just marking it here. There are more concept that other questions are also there. We will solve it. Which of the following is or are the disadvantages of a linear phase FIR filters design using window method and frequency sampling method? So option A is lack of precise control of the pass band and stop band edge frequency. Option B is computationally complex. Option C is relatively small technique of designing linear phase FIR filters. So the question is which of the following are the disadvantages of linear phase FIR filters design using a window method and frequency sampling method. So the disadvantage of the linear phase FIR filter is lack of precise control of the pass band and stop band edge frequency. So correct option is A. Okay. Okay. So now moving to the next question. Pole zero placement method is used to design an IR band pass filter which with the following specification. The specification is given as if the poles of the filter represented by r e to the power j theta determine the value of r and the theta, signal rejection at zero frequency 400 Hz, a narrow passband centered at 200 Hz and 3 dB bandwidth of 60 Hz and sampling frequency is given 800 Hz. So now we have to find out the poles of the filter that is represented in the form of r e to the power j theta. And also we need to determine the value of r and theta. Okay, so first it is given signal rejection at zero frequency, that is a 400 Hz. So all of you I think have gone to the lecture video. There is one question is also described. So zeros are placed at angle of 0 and the if this frequency. Okay, so now first we need to find out the zeros. So first one is a 0 and other place where it is defined, that is 2 pi by 400 sampling frequency. Okay, so that will be the pi at which location that poles are placed. So one is 0 and another one is pi. Okay, now we have to find out the poles where we can place the poles. Okay, so in order to the narrow passband centered frequency is given as 200 Hz. So poles should be placed at plus minus 2 pi. It is given in hertz, so we need to convert into radian and per second. So for that we have to divide that frequency by the sampling frequency. Okay, so you will get pi by 2, that is plus minus pi by 2. The poles are placed at plus pi by 2 and minus pi by 2. Now it is given that the poles, the coefficients of the poles should be a complex conjugate of that r e to the power j theta. Now we need to find out that theta is related to the bandwidth. I hope all of you have gone through that. This type of one figure is there where the bandwidth and other things are determined. So I really not remember this one. So I hope all of you remember, I hope all of you gone through the lecture video. So now we need to find out. So in order to find out that theta, there is a one formula is given pi by fs multiplied by bandwidth. Now pi is given, fs is 800 hertz, bandwidth is given 3 dB, bandwidth is 60 hertz. So multiplied by 60. So from here you will get 0.225. Okay. Now we need to take r is equal to e to the power minus bk in order to find out r. It is also one formula. So bk, it is a bk, it is not a theta, it is a bk. So e to the power minus 0.225, you will get 0.798. Okay, so r we have find out 0.798. So there is three options are there. R is equal to 0.79. Now the poles are placed at plus minus pi by 2. So theta will be the angle of pi by 2. So correct option is option C. Okay. In the pole zero placement method of is used to design an air filter. So poles and well, first we need to find out the location of poles and zeros and that angle at which poles are placed, that is pi by 2. Now we need to find out the bk and r value. In order to find out the r value, that formula is r is equal to e to the power minus bk. So from here first we need to find out the bk. The bk can be find pi by fs multiplied by bandwidth. Bandwidth is already given. So from here we get the bk, and by putting the bk value in this equation we will get r 0.798. Okay. Okay, I hope all of you got that question. So moving to the next question. Okay, so next question is determine the order of a low pass Butterworth filter with maximum gain of 10 dB and a cutoff frequency of 2 kilohertz at which the gain is at least 7 dB and a stop band frequency of 4 kilohertz at which magnitude is required to be less than minus of 30 dB. Okay, so now let's see what are the values are given. Omega p is given, that is 2 kilohertz. Determine the order of a low pass Butterworth filter. Maximum gain is and the cutoff frequency is 2 kilohertz. So that cutoff frequency is 2 kilohertz and stop band frequency is given as a 4 kilohertz. Omega s is given as 4 kilohertz. Now 3 dB down is given already, so epsilon will be 1 only. Yeah, you can take it as FP and FS also. But when you convert, there is a sampling frequency is not given, so you can take it. Okay, FP and FS you can define it. If you convert it, or you can directly put in the equation also. Okay. So what is the total attenuation in the stop band? That is minus 30 dB is there, and here the maximum gain is 10 dB. So total attenuation minus 30 minus 10, that it will be the minus 40 dB. Okay. So now in order to determine the order of the Butterworth filter. So it is written as like n is equal to already you know that what is the formula of order of the filter. Actually, in fixing you should writing that is log 1 by del 2 square minus 1 and the denominator that is 2 log omega p divided by omega s. So if you want to convert ft and fs is if you convert 2 pi by fs 2 pi ft divided by fs, but here sampling frequency is not given. If you put into the denominator, that will be cancel out. Okay, 2 log 2 log omega p or fp divided by fs. I'm writing okay fp divided by fs. So sorry guys, I'm not able to write actually clearly. So you can note it down like, so if you solve this question 1 del 2, if you change it that is minus 40 dB into 10t log del of 2, you will get 0.01, right? Ah, 20 log delta 2. Then if you solve here, already totally attenuation is given in the, already we have taken that minus. So if you calculate it, you will get 0.01. Otherwise, answer will get changed. If you take that minus, then minus minus will be cancelled. Then that will be the 1 by or 100 it will be. It depends. 20 log. Yes, yes. Continue. Depends on the options and questions. You have to choose it. Okay. So FP divided by FS. Hmm. So if you put all these values, actually I am not able to write on the screen. So if you solve it, if you are putting log, I am just uh, telling. So if you putting in this formula, the formula is log in brackets 1 by del 2 whole square minus 1 divided by 2 log omega p by omega s. If you convert it, it is given fp and fs is given, then all the terms will be cancelled out. So omega p divided by omega s, that you will solve this, you will get the order of the filter is 7 approximately. Del 2 is given 0.01, so 1 by del 2 with 10 to the power 4, right? 10 to the power 4 minus 1, that is 2 log 2. So if you solve this, you will get approximate value 6.64, that is equal to 7. Okay, and because n must be greater than equal to the this value, so that the value is coming 6.64, that will be equal to the 7. So correct option is option A. Option A is the correct answer. Okay. Currently, my screen is not working. Sorry, I lost my connection. So I hope I'm audible and visible again. So now next question is determine the order of type 1 low pass Chebyshev filter that has a 1 dB ripple in the pass band and cutoff frequency 1000 Hz, the stop band frequency of 1500 Hz and an attenuation of 40 dB or more. Okay. So now here stop band frequency, cutoff frequency is given and attenuation is also given. So now the type 1 Chebyshev filter formula already we know that is n is equal to log root of 1 minus del 2 square plus root that is del 2 square 1 plus 1 minus del 2 square in brackets 1 plus epsilon square and whole divided by epsilon del 2, okay, and divided by log in bracket omega s divided by omega p plus root omega s divided by omega p whole square minus of 1. Now here stop band frequency is given, that is omega s, or you can that say that fs is given is 1500 hertz and the cutoff frequency in the pass band is given fp, that is 1000 hertz, and here the sampling frequency is not given. So if you convert that fs and fp in the omega s and in the form of omega p, that is 2 pi fp divided by fs, the whole term will be cancelled out, omega s by divided. So you can put it like omega s fs divided by fp also here. Okay, you can write it fs and fp, fs and fp. So now in the pass band the ripple is 1 dB. So from there we need to calculate the value of epsilon, that is 10 log 1 plus epsilon square is equal to 1 dB. So from here if you find out epsilon you will get 0.502 if you solve this equation. Okay. Now in order to find out attenuation in the stop band, that is given is 40 dB. So 20 log del 2 is equal to 40 dB, that is minus 20. So del 2 will be, we will get it 0.01. Okay. So now all these values we need to put in this equation. So I am removing from here. So just remember all these values. So now by putting this equation you will get log root 1 minus del 2 is given 0.01 whole square plus 1 minus 0.01 whole square multiplied by 1 plus epsilon square, that you will get 0.502 whole square, you will get 0.259. Okay, and then divided by epsilon 0.502 and 0.01, and in the denominator you will get log fs divided by fp, that is 1500 hertz divided by 1000 plus root of 1500 hertz divided by 1000 whole square minus of 1. If you solve all this equation, you will get 6.205. Here the option is not given correctly. So if you find out, you will get 6.02. So there is a no option is correct. So correct is option is 7 approximately, or 6.7. Correct option is A, not C. Okay. Otherwise, you can solve it again and check it out if 4 is coming. When I have solved, that is coming 6.205. Okay. If it is a 6.205, then a correct option is option A, that is 7. Now, moving to the next question. The approximate integral as in equation 1 by the trapezoidal formula is given where t naught is equal to nt minus t and t is given, small t is given and capital T. Determine the expression of y of nt. So y of t, the equation 1 is given y of t is equal to t naught to integral of t naught to t by differentiation or dash tau d tau y of t naught. So as we know that the trapezoidal formula, that is, it is like given like this, f of x dx, then how we can write del of x divided by 2 and f of x naught plus f of 2 f of x1, like this. So if we are taking the trapezoidal formula, so a del of x is here t capital T by 2, and if we are putting or integrating this, so what we will get, y dash tau minus y dash tau plus y t naught, and it varies from t naught to t. Okay, so it is t by 2. If we are putting here, you will get y dash t minus y dash t naught plus y t naught. Now here it is given t is equal to nt and t naught is equal to nt minus of t. So it will be t by 2, y dash is given y dash, t is equal to 1t, so nt minus y dash, t naught is given nt minus t plus y of t is t naught is nt minus t. Okay, so from this option, the correct option is option C, that is y dash y of nt is equal to t by 2 y dash nt plus y dash nt minus t plus y nt minus t bracket t by 2. So just we need to solve this integral and put it t is equal to nt and t naught is equal to nt minus of t. Okay, so the correct option is option C, if you see that by after solving. Okay, so now moving to the next question. Next question is, convert the analog filter which system function in equation 2 is given into a digital IIR filter by means of impulse invariance method when sampling frequency is 500 Hz. So the system function is given in HA of S is equal to S plus 1 divided by S square plus 2S plus 3. Okay, so now we have to convert analog filter into a digital IIR filter by a impulse invariance method. Okay, so how we can solve this question? So the sampling frequency Fs is given as 500 Hz and T is equal to 1 by Fs, as we know that. So it will come T is equal to 2 into 10 to the power minus of 3. So first we need to find out the poles or the roots of this transfer function. So first solve this the denominator in order to find out the poles. So if you solve this, you will get S is equal to minus 1 plus minus j root 2. Now we have to solve this equation by a partial fraction. Okay, so now A is equal to S minus of 1, or if you write like this in the form of that in different part this equation in terms of poles, so you will get 1 plus 1.414 j, that is one pole, and the other pole is S plus 1 minus 1.414 j. The value of root 2 is 1.414. Okay, so now these are the poles, and it is not a it is a S plus 1. Now already you know that how to solve the partial fraction. So I am removing from here, then solve it. It is given as A divided by S plus 1 plus 1.414 j plus B divided by S plus 1 minus 1.414 j. If you find the values of A, you know that how to solve the for this. So in order to find out the A, so HA of S divided by the system function HA of S multi and with the one pole and putting S is equal to minus 1 minus 1.414 j. If you solve this by the denominator part is j S plus 1 plus. If you solve this, you will get A is equal to 0.5, and similarly if you solve for V is also you will get 0.5. Okay, after solving this, now we have to convert it into a Z domain after finding out the roots and solving it. Then what is will be the equation? I am removing from here. I am directly writing from here. You can check it. 0.5. The values of A and B is 0.5 divided by one pole and 0.5 divided by other pole. Now what we need to find the value of omega t, and you know that impulse how to solve the impulse invariance method, that is in the form of summation of t is equal to 0 to n, what is this, ck divided by 1 minus e to the power minus pk. Pk is the poles, that is in z inverse. Now we have to put in that form. So first we need to find out the and that is the j omega t, not a pk, that is j omega t. Now we need to find out the j omega t. Okay, so how we can find it out? As we know that a plus j omega or sigma plus j omega 1 plus minus 1.414 is given in the poles. So from here omega you will get 1.414, right? And t is also 1 upon sampling frequency. We will get 1 by sampling frequency, that is 2 multiplied by 10 to the power minus 3. We will get 2 multiplied by 10 to the power minus 3. Now in order to find out omega t, then 1.414 multiplied by 2 10 to the power minus of 3. Now we will get 0.00228. Okay, then if we will put into this form j omega t, then we will get e to the power j 0.00228. And if we convert it, so the correct option, that is 0.5, a and b value 0.5, and omega t we will get 0.0028. So the correct option is option a, we will get. Okay, I hope all of are you getting this question, how to solve this? Or should I repeat it once again? Okay, so now the other question is, convert the analog filter with system function in equation 3 is into a digital IIR filter by a bilinear transformation where sampling frequency is 1000 Hz. So here sampling frequency is given as a 1000 Hz, fs is given 1000 Hz. Can give the other slide? I don't have. Okay, so I am solving it here. The sampling frequency is given, fs is equal to 1000 Hz and t is equal to 1 by fs, as we know that. So what we will get, 10 to the power minus of 3. So in order to convert analog to into digital domain by linear transformation, we know that we need to put at the place of s, the formula is 2 by t 1 minus z inverse divided by 1 plus z inverse, and this system transfer function is given as h of a of s plus 1 divided by s square minus of 4. So now in order to convert it into a z domain, put in the place of s that equation. Okay, so now here t is given 10 to the power minus 3, so it will be 2 into 10 to the power 3 1 minus z inverse 1 plus z inverse. Okay, so we can put it 2 into 10 to the power 3 1 minus z inverse 1 plus z inverse plus 1 divided by 2 into, so it will be 4 into 10 to the power 6. Here I am taking out it from here, 1 minus z inverse 1 plus z inverse whole square minus of 4. Okay, if we take z, if we can write it into this form also, 1 sorry z minus 1 or z plus 1 by taking z out from this, so from the lower also 4 into 10 to the power 6 z minus 1 or z plus 1 whole square minus of 4. Okay, so this is the equation. Now which one is the correct option? So match from there, already we have solved in this form. So 2 into 10 to the power 3 z minus 1 divided by z plus 1 plus 1. 2 into 10 to the power, here I have taken out of this bracket. So if you take it into the inside bracket, so 2 into 10 to the power 3 10 z minus 1 divided by z plus 1 ka whole square minus of 4. So correct option is option B. Okay, here directly just we need to put the value of s in terms of z, and in the bilinear transformation already we know that the formula, that is 2 by t 1 minus z inverse divided by 1 plus z inverse. Okay, okay, so now moving to the next question. An ideal analog integrator is described by the system function, that is h of s is equal to 1 by s. A digital integrator with system function h of z can be obtained by using the bilinear transformation. If the sampling frequency is 400 Hz, determine the difference equation of the digital integrator relating to the input xn to the output y of n. Okay, so here sampling frequency is given as fs is equal to 400 Hz. Now first we need to calculate t. So 1 by fs, that is 1 by 400 Hz, and t you will get 0.25 multiplied by 10 to the power minus of 2. Now ha of s is given 1 by s, and also we know that ha is output divided by input, so 1 by s. So from here we will get s y of s is equal to x of s. So from here, if we convert into the time domain, so we will get xt y dash of t, right? Now already we know that in order to transform in the z domain by using the bilinear transformation, so already we have solved y of nt is equal to t by 2. We know that this equation also, y dash nt plus y dash nt minus t plus y nt minus of t. We know that this equation. Now by putting in this equation y of nt, t is given 0.25 into 10 to the power minus 2. So 0.25, if we take 10 to the power minus 2 down, then 2 into 10 to the power 2. Okay, so y dash nt, here y dash nt is equal to xt. So we have to put x of nt. Now I am writing here plus x of nt minus t plus y nt minus t. So I am removing from it here, from here. So if we write it into generalized form, so what we will get, y of n if we remove the t, and 1 by 4, so it will be the 1 by 800, or we can write it 0.25 divided by 2 or 0.1 to 0.125 into a form of x of n plus x of n minus 1, we are taking t outside, plus y n minus of 1. Okay, this is the equation y of n minus of 1. Okay, so now we have solved, or we can write it into this form 1 by 800. What we will get? 0 10 to the power minus 4, 0.125 into 10 to the power minus 2 and multiplied with all the components. So if you solve this, then we will get which option? 10 to the power 0.125. It must be 0.125 from here. Just I am removing from here so we can able to or match the options. Okay, so that must be 0.125 10 to the power minus 2 x of n 5 and in this form. So there is, I think, no correct options are there. So it will become 0.125 10 to the power minus 2 x of n, 0.125 x 10 to the power minus 2 x n minus 1 plus 0.125 y n minus of 1. Okay, so you have to solve it. There is no correct options are there. Okay, are you getting these questions, or are you having any doubt? Or we can move to the next question. Okay, so moving to the next question. If h of s is equal to 1 by s square plus s plus 1 is represent the transfer function of a low pass filter, not a Butterworth, with a pass band of 1 radian per second, then what is the system function of low pass filter with pass band 10 radian per second? So h of s is given as 1 by s square plus s plus 1 at pass band of 1 radian second. Then if we want to determine the pass band at 10 radian per second, then what we need to do? We need to put in the place of s by 10. So by putting, we will get the pass band at a 10 radian per second, that is 1 divided by s by 10 whole square plus s by 10 plus 1. So s square divided by 100 plus s by 10 plus 1. If we take 100 out, if we solve further, then we will get s 100 divided by s square plus 10s plus 100, right? So the pass band at 10 radian per second, we will find the h of s, this one. So correct option is option A. Okay. Okay, I think all of you have got this. So can we move to the next question? Okay, so next question is, when sigma is equal to 0, then what is the condition on R? Okay, so already we know that Z is equal to R e to the power j omega. We know that this condition, and S is equal to sigma plus j omega. Now, if sigma is equal to 0, then S is equal to J omega only. Okay, and from this equation, Z is equal to R. What is the e to the power j omega? Cos omega plus sin omega. J sin omega. So if we put sigma r is equal to 0, then whole function will be 0. So it must be r must be equal to 1 in order to find out the, or in order to satisfy this condition. So r must be a 1. Okay, if sigma is equal to 0, then r is equal to 1. Okay, so I hope all of you got this. For this week, this is the last question. So the question is completed. If anyone of you have any doubt, you can ask. Otherwise, we can close this session. So thank you everyone for joining. Anyone having any doubt? Hello. Hello. Yeah, I'm audible. Are you able to listen me? Okay. So now we can close this session. So thank you everyone. Thank you for joining. Now we can leave this session. Okay.